So this is the very concise summaries for studying the prismatic shafts under pure torsions. So basically, for this problem, in this model, we assume an arbitrary shaft with an arbitrary but uniform cross sections, and that one we assign the z-axis in the axial directions, and xy to express the cross-sectional plane. Okay, so that is assignment here. A pure torsion basically is a couple of torsion can be applied at the two ends, or for simplicity, you can assume the bottom face fixed and in all the degree of freedoms, and only top is under torsion. Usually this scenario, say fixed at the bottom, only twist on one side will be easier to comprehend. So here I put the torsion like this here. Again, we have three assumptions. The first one is the point, any point in any cross sections is under rigid body rotations, and that one leading to the formulation of the displacement vectors, in particular the two components here. The x component and y component are based upon these assumptions, or the points on the cross sections doing the rigid body rotation. So from there we can derive this one. And for the third displacement in the third dimension, it's called the W, that's called the warping, warpage or warping. And we assume the warping is only the function of point in the cross section, but doesn't affect it by the level. So that means if there's a warpage occurs at any cross section, the warpage is the same with the other one. Okay, so that is another assumption here. The third assumption is beta. The beta is called the rate of the twist. Basically, beta is saying if we would be able to figure out the angle of the twist on the top, then we simply divide that angle of twist by the length L, by the torsion length L, and that is the beta. And beta here is a constant, but beta is the magnitude determined by how big the torsion is applied together with the dimension and material properties. So here, if you like to make note, beta is a constant to be determined. Okay, usually we are given is this. We are given a magnitude of torque, and we given the size of the dimensions, geometries of the shaft, and here we're looking for beta. That is the first value we need to find. Once the beta is solved, then we want to follow up is to determine what is the displacement, what is the strength. In particular, we want to calculate what is the stress. Okay, that is the final things we want to determine. And once we determine the stress in the general way, then we want to answer the question where the maximum stress occurs. From there, we're going to design the problem. For example, we wish the maximum stress won't exceed the allowable stress we designed. So that is the more kind of applications. Okay. So that's the problem formulations. And to this point, to help us to solve for beta, and we're going to use boundary conditions. And let me talk about this one. This equation basically is on the equilibrium on the top surface. Basically, this top surface is here. Okay. All the small, at this point here, we have small elements, and this is tau zx, and this is tau zy. Due to the two stress components applied onto this small stress element, and we have a small torque. We integrate such a small torque over the whole cross-sectional area, we have this formulation. This one must be in equilibrium with the given torque here, okay? So from this point onward, we simply plug in the detailed expression of the stress here. And again, to this moment, we have two unknowns at this moment here. Beta, we don't know what is the value, and we don't know what is omega. To implement this integration, we need to know the two numbers. Otherwise, or on the other side is saying, only given this one equation, we wouldn't be able to solve for two unknowns. Okay, so here basically there's one equation, two unknowns, and that one we might need additional information, and that is come to this boundary condition here. For this boundary condition, basically is apply the cosys stress, and to come up with this one here. Okay. And basically here, if you implement this one, multiply with n is any normal vectors, and apply to the xy plane, you will come up with this one. Okay. Again, this formula is we call the cosys stress formula. Okay, so we have this one here introducing the contents of the stresses into here. Okay, and this is the format one. And really depends on the convenience of the given information. Sometimes we take the format one. The L and M are simply the directional cosines of this n, and so basically that is the components of uninormal vectors. And sometimes, depends on our convenience, we like to take the format 2. Okay. If sometimes we are given the normal vectors in terms of I would say the tangent component here, dy ds, dx e ds, this kind of the tangent component will calculate the differential things. If we have the convenience information about the two quantities, then sometimes we take the format 2. Okay. The second format basically equivalent is like this one. So this one is more commonly used. Let me highlight. This is the second format, and this is the first format. Okay, depends on the given information. Sometimes this is convenient, sometimes this is. And for this one, we look into a little bit more detail here. So this is beta. For example, for these equations, we have beta unknown, and we have unknown W here. So basically, in theory, together with this equation and this equation, we should be able to solve for beta and W together. Okay, and in theory, we could, and how to, in practice, to solve for this one, need a little bit more explanations here. So for this, I'm going to talk about the solution strategy, and Mark, we can stop a little bit here.